Hi everyone, I'm Jundu from National Engineering Lab for Speech and Language Information Processing in University of Science and Technology of China. On behalf of the whole team, today I will introduce the details of our systems for CHiME 6 challenge. First, let me introduce our great team. Most of them are from USTC, including Dr. Yanhui Tu, Mr. Lei Sun, Ms. Li Chai, Mr. Xin Tang, Mr. Mao Kui-he, Mr. Feng Ma, Dr. Jia Pan, Dr. Zhenqing Gao, Mr. Dan Liu. Also, we have the Professor Qinghui Li from Georgia Tech and Professor Jingdong Chen from Northwestern Polytechnical University. Before introducing the details, we give an overall comparison of techniques we adopted for CHiME 5 and CHiME 6. CHiME 6 uses a new array synchronization method, which significantly improves the data and label quality. And this new setting, we found that our previous front end, namely two-stage speaker-dependent speech separation, which worked well for CHiME 5 data, had no advantage over the simple GSS method for CHiME 6 data. Accordingly, we developed new front-end using modified GSS and beamforming GSS, namely MGSS and BGSS. For acoustic modeling, we use more advanced network architecture, including ResNet, TDNF, Res BLSTM with self-attention and dilation modules. For system fusion, we use the MBR combination, proven to be more effective than state posterior average and lattice fusion. For the new speaker dilatation part in track 2, we use the neuron beamforming-based speech separation for pre-enhancement, followed by ResNet-based X-vector extractor and spectral clustering for speaker dilatation. First, let me introduce our work for track 1. This is a system overview for the training stage. For front end, we apply GSS and our MGSS to the far-field data to generate the separation data. With the one data and the separation data, we further do speed perturbation, volume perturbation, and spec augment as the training data augmentation. For backend, we design two types of acoustic models, namely single-feature acoustic model and multi-feature acoustic model. In total, we have 6 acoustic models for the model fusion. In the recognition stage, we adopt a novel two-stage mask estimation method using MGSS and BGSS, which will be introduced later. Then, with different front-end output and different acoustic models, we do the ASR decoding and fusion to generate the final recognition results for rank A and rank B. To implement all the modules, we use multiple platforms for different purposes. We use the official KLD toolkit to implement GSS, acoustic models, language models, and model ensemble. We use PyTorch to implement the neural network-based speech separation models. Also, we have self-developed tools for CA-CGMM and beamforming. Now I will introduce the detail of our front end, namely MGSS and BGSS. Our modified GSS is motivated from original GSS. We use the same WPE and CA-CGMM implementations. Here, CA-CGMM has 5 Gaussian mixtures corresponding to 4 speaker sources and 1 noise source. Our MGSS are different from GSS in several aspects. First, we use GVD beamforming as adopted in our CHiME 5 system. In addition, we also perform online beamforming by a mini-batch setting. Second, we use the signal to interference plus noise ratio to select single best array or several best arrays as a supplement to the multi-array data. The online beamforming and beamforming for selected array data can be used for front-end fusion with beamforming in the offline multi-array setting. To further improve the mask estimation for CA-CGMM-based beamforming, we use the second stage to refine the mask estimation. Here, we use the beamformed data after MGSS for 4 target speakers, namely STFT features of each target speaker, to calculate the log power spectral features of each target speaker and the interface differences between different speakers. With these features as the input, we train an LSTM network to learn the new masks, which are used for the second stage MGSS. This slide shows the training data generation for BGSS model. Using the far-field training data with the time annotations, we can generate the target speech, interference speech, and estimated noise using LSA for each speaker. Then we simulate the mixed speech followed by MGSS. The beamforming data after MGSS are the BGSS model inputs, while the weights of the beamforming are used to obtain weighted versions of target speech, interference speech, and noise, which are adopted to compute the masks as the learning targets of BGSS model. Please note that this procedure generates the input and outputs for one target speaker. All the 4 speakers in one session are in turn considered as target speakers to generate all inputs and outputs for BGSS model. To implement BGSS model, BLSTM network is employed with 2 BLSTM layers and 1024 nodes for each layer. To optimize the parameters of BLSTM model, the mean squared errors between estimated and reference masks for 4 speakers are minimized. Here we give a speech demo for the comparison between different beamforming methods. We can see that the official beam format cannot suppress the interfering speaker well. GSS can achieve good suppression of speaker interference with the price of yielding more residual noises. Our 2-stage MGSS plus BGSS approach can further perform better denoising over GSS. This figure shows the word error rate comparison between multi-array GSS and our front end with different settings. Overall, the online beamforming for selected array data using our MGSS plus BGSS approach achieves the best performance, yielding an absolute 3% word error rate reduction over GSS approach. By using MBR fusion of our front-end processing, and 4 different settings, an additional gain of absolute 2% water error rate reduction could be observed. Next, we move to the backend. The configuration of data augmentation is shown in these slides. We use 192-hour WAN data, 96-hour GSS data, and 64-hour MGSS data. The total amount of training data is 352 hours. The volume perturbation and the spec augment are applied for all data without increasing the data size. For acoustic models, we design 2 types, namely the single feature AM and the multi-feature AM. The single feature AM uses the conventional 40-dimension MFCC feature with 100-dimension I vector. The multi-feature AM is our new invention. The motivation here is we not only use the features for the target speakers, but also the features for other 3 interfering speakers, including the feedback features and IPD features. For the model architecture, 4 types are used with different combination of ResNet, residue BLSTM, TDNF with self-attention and dilation setting. All 4 networks are applied for multi-feature AM, while only 2 networks are applied for single feature AM. In total, we have 6 acoustic models. All these models are optimized by lattice-free MMI. Here we show the detailed architecture of one network for the single feature AM. For multi-feature AM, we have 2 branches corresponding to the 2 parts of multi-feature input. In each branch, the features related to other 3 interfering speakers are concatenated. The details of other 3 networks are also shown in the next 2 slides for your reference. In this slide, we compare the water error rates of different acoustic models. Here, the official acoustic model does not use the data augmentation, while other acoustic models use the data augmentation. We can see that with training data augmentation and better network architecture, our best acoustic model can yield an absolute water error rate reduction of more than 10%. Using the MBR fusion, the overall water error rate on the development set can be reduced to 30%. Finally, we list our submitted results. Here, the overall result on the development set for rank A is worse than 30% mentioned in previous slide. This is because we do not finish all the multi-fusion experiments on the development set until the submission deadline. As most of our efforts are spent on the track 1, we do not have enough time for taking a deep dive into track 2. Accordingly, we design a relatively simple procedure for track 2, including enhancement part, diarization part, and ASR part. In the enhancement stage, compared with track 1, a new module called NBSS is built to initialize the masks of CA-CGMM, which will be introduced later. The speaker diarization uses the X-vector extractor and spectral clustering. Finally, with the 6 acoustic models in track 1, we perform MBR decoding and fusion to get the final recognition results. The neuron beamforming SS model here is to estimate the masks of 4 speakers in each session. NBSS model is similar to BGSS model in terms of input LPS and IPT feature type and output masks. The main difference is that the inputs of NBSS model are original multi-array speech rather than the beamformed data in BGSS. Another problem here is we need to perform the target selection after beamforming, as we do not have the speaker labels as in track 1. Here, we use the speech duration of beamformed data as a measure to select the target. This is a procedure to generate training data for NBSS, which is also similar to that of BGSS. These slides show the details of ResNet-based X-vector extractor and spectral clustering. From our submitted results, the current pipeline for track 2 does not work well. There is a huge performance gap between track 1 and track 2. We will explore more in the future. That's all for my presentation. Thanks.